Yeah, I've restarted the recording, so I think we're good to go.
Yeah, did you stop?
Yeah.
Can you also close the transcript?
Oh, also get rid of the transcript, right? Okay, yes. I'm going to have fun reading that transcript.
Pretty accurate, right?
It's getting better. The good one I had during the pandemic, I was teaching a course that involved diffusion and drift, and so I was talking about Smolakowski equations, and Microsoft Teams transcribed that as some other cow's guy equation. So I don't know who this other cow guy was, but okay. So predictably, that finished as soon as we broke. So I've now got a pretty good estimate of the density of states. My histogram isn't flat currently at the point I happen to stop the simulation. And I would normally run this for quite a bit longer. I would get f down to 10 to the minus 10, 10 to the minus 12. I've stopped it at 10 to the minus 4 here. But provided what I care about is just the energy histogram, because I know the density of states, because I know the Boltzmann factor, I can reconstruct, given the density of states, I know it in this discretized way across my energy bins. I can construct an energy histogram at any temperature, so I can construct the mean energy, and I can construct the variance in the energy. So why is that taking so long? Oh, I've set it running again. That was stupid. Let me stop that. There we go. So I haven't had to run a second simulation with fixed weights because all I care about is the energy distribution at the moment. So I've got out my histograms, I've got out my mean energy, and I've got out my heat capacity. So as with a multi-canonical sampling, if I also care about something that isn't energy, I can do the same trick. I can run a simulation with a fixed density of states. During that simulation, I can sample the other things I care about. And then because I record the energy with those samples, I know what the probability of that sample would be at any temperature that I have energies for. So I won't bother doing that because it'll look exactly the same as when we did the multi-canonical sampling. So that's it. I can, given something else that I can sample, I can weight those samples accordingly and do that as a second step with a fixed density of states to get information on anything that I care about that I can compute as a function of positions across the temperature. So I'll skip that in the interests of time because I want to get on to the last method. But yeah, here's one I did earlier, doing the same trick we did with the multi-canonical sampling, compute the heat capacity from reweighted energy samples versus computing the heat capacity by just reweighting the bin heights or constructing the histogram using the density of states and the Boltzmann factor. In fact, this time I don't have the disagreement at low temperature, I have it at high temperature. Maybe I've just, my convergence error is having a different effect in the multi-canonical sampling as in the Wang-Landau. Neither of the calculations I showed you were particularly well converged. So any questions on Wang-Landau sampling before I move on to the last thing? Yep.
Why do you need to kill the histogram? Is it just because they have to choose that?
I mean, why don't I keep the information?
Like if you have to try, if you put it in head, right, it's like well, decreasing it, but slowly now, then the new version of the histogram is kind of like take the old one, like the standard.
Yeah, so people do that actually. So in fact, people tend to do a mixture. Is they'll kill the histogram for the first few iterations because it's going to be, it's been constructed with a terrible density of the states and it's biased. But as your density of states gets quite good, people will stop killing the histogram. And then rather than using a fixed F to update their estimate of the density of states, they'll use an F that decays as 1 over the current number of Monte Carlo trials you've done. So that decays as 1 over number of trials and gets smaller and smaller with time. And you don't throw away the histogram. But that histogram is not much use for reweighting quantities other than the energy. We don't need it to compute energy distributions. You just need the density of states. But for like the end-to-end length here, I guess I could say I'm going to use that histogram and reweight the samples that I generated in it. But the weight then depends on time because I'm still changing the density of states while updating those samples. So you could do something where you say, well, okay, I'm very nearly converged. I don't care that my W, my weight factor for each sample is changing slightly with time. I'll just take it as being the weight from the final density of states. And you probably get something that was mostly okay. But yeah, strictly speaking, if you don't have static weights, then that reweighting becomes inaccurate.
Are there converted results for that? Like if you go your basis program, like stationarity somehow, you do it somehow.
There's a little bit of literature on that. So some people call this the 1/T method. So T being time, how many samples I've done, and showing that decays. There's some work actually from Mike Allen here at Warwick before he retired on refinement to that 1/T method. When some people get F down to 10 to the minus 22, you know, they go absolutely nuts and make, because if you're really interested in knowing very precise natures of phase transitions. And in principle, people do this in 2D as well, so they'll map out density of states in energy and volume, say, and then you can literally just do a contour map of the heat capacity, and you see, oh, there's the phase transitions, because those are the large peaks that would converge to a delta peak in the large system limit. So you can literally just draw the phase diagram by giving me a heat map of the heat capacity. And you want very sharp, accurate phase boundaries in some cases, so they go all the way down to very, very small F. Michael.
How do these two approaches typically compare?
Yeah, it's one of these things where a bad implementation of one will be worse than a good implementation of the other. Wang-Landau is very popular, which to me suggests it's probably slightly more efficient. I guess if what you care about is just getting the heat capacity to build these maps, then you would do Wang-Landau, because then you don't need the second stage of doing a long simulation with fixed weights. So you're already cheaper that way. Parallelism, again, I can break up the energy range into windows. I can compute the density of states in each window. I can match them together at the boundaries of the window and get, in principle, a superlinear speedup if I do it that way. Okay, so last thing, as I said at the start, this is the method I'm now trying to, all of my old toy codes and actual research codes. A colleague, actually it was Nigel Welding at Bristol, for those of you who know Nigel, spoke to me at a conference once and said, "Why are you still doing Wang-Landau recursion, David? That's dumb. You want to do transition matrix Monte Carlo? It's much better." And for years I thought, yeah, I'll get around to that at some point, Nigel. And when I did get around to it and got it working, I went, oh damn, right. He really should have nailed me to the floor and said, no, seriously, do it now. It converges much, much faster and has a lot of nice advantages. So what do I mean? What are the deficiencies I'm trying to address with transition matrix Monte Carlo? So some people have already mentioned, I'm throwing data away. So both in the multi-canonical sampling and the Wang-Landau sampling, I'm doing these cycles, these iterations of updating weights or the density of states estimate, and I'm throwing away the samples that I used at the previous iteration. So that's wasteful. It would be nice if I could do something with those samples and not have to throw them away. So that's part of it. The other part of it is all the methods I've talked about for building up a histogram, a probability distribution, are what you might call a visited states method. I'm counting how often I visited each state in order to build up an estimate of the probability distribution as a function of energy, how often I visited each energy macrostate. This isn't going to be a visited states method. This is going to be a transition matrix method. And I'm conscious that Manon mentioned transfer matrix. Correct me if I'm wrong. I think the difference between transfer matrix and transition matrix in this context is transfer matrix is going to be number of microstates by number of microstates and tell me the probability of going from one microstate to another. Whereas the transition matrix, the thing I'm dealing with, just a name, is number of energy macrostates by number of energy macrostates. So I've got 50 bins, it's 50 by 50. Whereas the transfer matrix would be enormous. It would be something that's too big to deal with. Okay, so the visited states methods have some problems. There's this burn-in problem that I've not mentioned, that Really, I should be letting my sampler equilibrate and then throw away the equilibration period. So I'm throwing away some samples there. And also I've got this problem that if I'm traversing up and down the energy range slowly, as I mentioned before, unless I'm running for a time that's very much longer than that traversal time, many, many times longer than that traversal time, you know, I might get some bias in my estimate based on just where I cut it off in that process, where I stop it sampling. So if it's going lots of time over here, lots of time over there, it's only done that 2 or 3 times, and then I kill it, I'm going to be biased to one side or the other. Just having mentioned that, there is some work out there on, in these situations, flat isn't optimal. You should have a non-flat distribution that somehow takes into account of the effective diffusion coefficient of your sampler as you go up and down the energy range. But transition matrix is another way of dealing with that. So because we're not computing our estimates of the probability by counting how many times we visited a particular state, we're not going to be vulnerable to that problem. So the idea is we're going to use this thing called the transition matrix. So the transition matrix is it's a matrix. That I should be a subscript. Apologies. In fact, one advantage of doing live demos is I can fix that. So the element of the matrix Tij is the probability that our algorithm, our sampler, will if it makes a move that starts in energy bin I, it will move to energy bin J. It will accept a move to energy bin J. If I know T, well, how do I know T? So the way the algorithm works is I just run my standard Metropolis sampler. I'm gonna have some bias weights to make sure that I sample all the energies that I care about. But every time I make a move, I'm going to update this thing called the collection matrix, which is the same dimension as the transition matrix, by adding in what was the probability of accepting the move that I've just proposed. So if that's a move from bin I to bin J, I put that in the collection matrix, row I, column J, and I add it to what was there already and start with 0. I also add the probability of staying where I am. So I add along the diagonal of that matrix the probability of rejecting the move. So I'm building up an accumulated average of the probability of, given I'm in bin I, that I move to bin J with a move, or I stay in bin I, which is along the diagonal. Please.
This may be obvious to everyone. We're talking about probabilities of transitioning from I to J.
Yeah.
There is a time horizon in class. Obviously, that's
yeah, so it's the probability at the next iteration, the next move.
And move the fidelity that you have, so these probabilities.
So I'm not doing dynamics here, I'm doing Monte Carlo. So I'm proposing a trial move that's the displacement of a bead. And I'm saying that if I pick a bead at random and I move it by a random, so if I pick bead, actually what bead it is doesn't matter. I pick a bead at random and I pick a displacement at random, then, well, okay, maybe I should define this, I define P first. So P is a vector that gives me the probability of being in each energy bin. If I apply the transition matrix to P, it's saying how will P evolve if I do one Monte Carlo move. Okay. Yeah. There's no time here. Yeah. Okay, so if I go from, I have this vector P, which is the probabilities of being in each bin. I apply the transition matrix. That takes me to P prime, which is the new probability of being in each bin after doing an average Monte Carlo move, if you like. So if you think about applying that transition matrix to P many, many times, I'm effectively just doing power iteration. Okay? I'm applying a matrix to a vector many, many times. That will converge P to the eigenvector corresponding to the dominant eigenvalue of T. Okay, and then I'm at equilibrium. I've then got a stationary P. This becomes an eigenvalue equation. P prime becomes P. And then if I can find the eigenvalue that corresponds, sorry, the eigenvector that corresponds to the dominant eigenvalue of T, I've found the equilibrium probability distribution. And so the advantage there is I'm not using a visited states method. I'm using every single move that I've done in the entire procedure. If I'm biasing to get me to sample the full energy range, that's fine. But when I update my transition probabilities, when I update my collection matrix to accumulate this average, the average elements of T, I use the unbiased acceptance probability. So I use the acceptance probability I would have if I didn't have my bias V, my multi-canonical bias that was pushing me to be everywhere. So what I'm building up is the T for the unbiased dynamics during biased dynamics. Yeah, they're at some temperature and they're biased, yeah. And the unbiased dynamics would be the equilibrium for that temperature, or would reach equilibrium for that temperature. Any questions on that? Yeah. Yeah. But then, 50 bins is a lot, to be honest. So 50 by 50 is, who cares? You can diagonalize that matrix like that. So
it would be very surprising if that were more expensive than running. It might turn out.
yes, yeah. I mean, you'll see. It's it just click of the fingers, it happens. Yeah. Oh yeah. I have to run a simulation to get T, but I'm using every single move in that simulation. I'm not having to throw away equilibration. I'm not having to throw away things from earlier refinement cycles of the weights, because I'm not using the biased probabilities to update T. I'm using the unbiased probabilities, and they don't change as the bias changes. So I can use everything. I can use every single Monte Carlo move. Okay, so the procedure is going to be, I'm going to run just like I did in the first worksheet, standard Metropolis Monte Carlo initially, so no bias. I update the collection matrix, which is the thing I need to average to get T at every move using the unbiased accept and reject probabilities. Periodically, and how often you do this is, a matter for investigation, I guess. Stop, look at the collection matrix, turn it into a transition matrix by averaging all the entries, diagonalize it, find the dominant eigenvalue, find the corresponding eigenvector. That is then your estimate of the equilibrium probability at the current temperature. Use that to construct multi-canonical weights that are going to push you to explore the full energy range. Add this bias into the sampling, go around again. But a key step is that what I'm accumulating in the collection matrix is the unbiased acceptance probabilities, not the ones that include the bias weights. There is a wrinkle in this that I should mention now. I have to be discretized for this to work. If I try and do some kind of kernel density estimate for the bias function, this will fail. I have to have the bias function for all states in bin I and all states in bin J to be the same. Otherwise, my estimate of the transition matrix will be biased towards certain states within a bin, and it all falls apart. I mean, it works, but you get slightly wrong distributions. And just as an aside, I'm going to do this in the context of multi-canonical sampling. I am doing Metropolis MC. I could do transition matrix Monte Carlo, where my acceptance probabilities that I'm putting into the transition matrix are the ratios of densities of states, and I do Wang-Landau transition matrix Monte Carlo. I combine those two and get the best of both worlds. But that's not what I'm going to do here. Okay, so define my polymer. This is the key function that I need that's new. So I take in Tm, which is my collection matrix. It's where I'm accumulating the accept-reject probabilities for moving between bins. I normalize it to give me a transition matrix that I'm calling norm Tm here. I guess part of the reason why this method wouldn't have been popular 15 or 10 years ago is your average statistical physicist doesn't know how to use LAPACK and fight with converting C calls to Fortran calls in order to get an easy way to diagonalize a matrix. These days, courtesy of Python, one line of code. It's much easier than it used to be. So find the largest eigenvalue, give me that index, and then my estimate of the equilibrium, the stationary probability distribution, is the corresponding eigenvector that corresponds to that dominant eigenvalue. And then I just do exactly what I did when I was taking a probability distribution and using it to construct an estimate of the weights. I'm just now using the eigenvalue of the transition matrix as the probability distribution. Okay, so now I'm going to do, I need some number of cycles. I'm again going to do, start setting up the simulation. I'm again going to do 5 cycles of 1,000 frames each. Now I know how long that's going to take. I might just make that a bit shorter. No, that's not shorter, that's longer. There we go, that's what I meant. For each cycle, I'm running some number of frames, where a frame is a number of sweeps. After I've run that many frames, I take my estimate of the transition matrix, and I use it to build a new bias. And I go around again. So this is going to be slightly more crowded than previously. I might have to zoom out a bit. So when I build my transition matrix, you'll see a heat map here of the initial versus final state. This is my current bias, which is currently 0 because I haven't built one yet. I haven't yet got an estimate of the dominant eigenvector of the transition matrix. So this is just the equilibrium probability distribution at the temperature that I'm running at. I'm going to use that histogram for nothing. Okay, this is just showing us how the range of energy I'm sampling is going to evolve as I build the weights from the transition matrix. But I'm not going to use that histogram for anything at all. And now I'm in that situation again, where if I scroll down to see how long until the iteration ends, we'll almost certainly miss the interesting bit. I said 500 sweeps, right? Shouldn't take too long. So as a preview of what comes next, I've then got a probability distribution from that eigenvector at the current temperature. Oh, it's happened already. Okay, so this is my current estimate of the transition matrix, and you can see it's populated the entire range more or less because I've done this trick with where I haven't got any samples. I've set that to the minimum number of samples I've got everywhere else just to avoid numerical errors. That won't make any difference. This red line is my current estimate of the dominant eigenvector of the transition matrix. So it's the probability distribution at the temperature I'm running at. And then these are the Boltzmann inverted weights that have come from that probability distribution. And you can see it already looks a lot like the weights that we were getting 2 or 3 iterations into the multi-canonical sampling procedure. And we've done shorter iterations because I was being impatient. Because I was being impatient, we've got this problem, is we didn't have any, we've ended up biasing ourselves to stay in that one bin. I'm hoping that will heal, but it might not. But it might not heal fast enough for the purposes of this demo. But once this is all done, did that just update? I can check, I can scroll down. Oh no, that's fine. Right, there we go, we're going. So that red eigenvector gives me the probability at the current temperature. Once we're done, I will know that probability at the current temperature to very high accuracy over the full energy range, even where it's essentially 0, right? As long as I'm not running out of machine precision. Where it's very small, I know it everywhere, and then I can just reweight it to other temperatures. So at no point have I thrown anything away. I'm getting sampling across the full energy range. I've already got a set of refined weights that look better than the multi-canonical weights that took a coffee break to compute. So I'm using all of the information I'm accumulating. Everything that I've done, every Monte Carlo move I've done is contributing at this point. We're getting pretty flat sampling already. So this, it works remarkably well. Of course, you shouldn't take my word for that. That might just be this particular toy example it works very well for. But the argument that you're not throwing anything away is the key one. You're using all the information, so you will converge faster. and also you don't have these transient and effects where you might be stopping the sampling at exactly the wrong point, so that you've got a bias. I guess one thing to observe is this matrix is very nearly diagonal. It's not very. It's a thin band, so we're only making moves from one bin to either its first or second neighbor bin.
Does it help you expand kind of the rather moves that normally when you just too complicated to dig and rejecting it? Like, that's the problem. Would you say this helps you come up with?
Well, the rejected moves are contributing, of course. So yeah, even if I reject a move, I'm the probability that I'm accepting or rejecting that move goes into the transition matrix and contributes to that estimate. Yeah. So it's sort of better than a visited states method in that way, because in a visited states method, it's only really the move that, well, if I reject the rejected move counts. If I accept the accepted move counts. Whereas here they both count. How much longer do I leave this to run? Well, we've nearly done 4 iterations. I might let it finish this time. So I'm very nearly done once this is done. So the reweighting, yep.
Sorry, how would you pair something like this with HMC? Would you just directly replace the forward step?
Very good question. Yes, that's something I meant to mention. So if I'm doing HMC, there's a slight problem there in that I'm putting in computational effort to evolve a trajectory, and then I'm only updating the transition matrix at the end of that trajectory. So it might not be a great idea to pair this with something like HMC because of that. I don't know if people have tried it, but yeah, that would be a potential concern, that if the bulk of my CPU time is going to generating the trajectories, then yeah, each one of those trajectories is only going to update the transition matrix once. But I've put a lot of work into generating them, so that might not be a great way to go.
I think there's probably pretty natural ways of using trajectory.
Mm.
Use sort of sample, right? Yeah, there's sort of tricks that are.
If your trajectory, in my language, has a thermostat, then you're also generating canonical samples. So for a visited states method, it'd be quite easy to do something, but for can you work out for a step in a evolution of a Hamiltonian dynamics what the probability of making the step is? It's a bit.
Yeah. Something that can describe outside.
Yeah, I'm sure there are things you can do. If I was going to go down that kind of route, if I wanted to do a hybrid Hamiltonian dynamics and Monte Carlo thing in this context, I would do force biased Monte Carlo rather than hybrid dynamics, and then that would be every force biased step would give me an update of the transition matrix. So that's finished. Thank you for asking exactly the right number of questions. Okay, and then I've now got this very accurate probability distribution at 1 temperature. It includes information from the entire energy range. Okay, so I can just reweight importance sample, to use the language, that distribution to other temperatures. From that, get the mean energy. From that, get the heat capacity. So let's just do that. Why is that taking so long? Have I crashed my notebook server? That one did finish, didn't it? It did, yeah. Just thinking about it, just thinking about it. Please don't tell me the notebook server has crashed. I don't know how long to give it before I give up. And if I'd been really smart, I would have saved the transition matrix so that I could just regenerate it. I can always just interrupt it and try running it again. Yeah. Stop. Yeah, it's not letting me stop it. But it was the very last cell in the top. Yeah, please do. Let's wait it out and cross our fingers. Yeah.
So I think like it's a bit similar to this, we're calling the eigenvector method. But guessing will be.
Yes. Yeah, I guess so.
With what you're showing, the difference to what I remember is you're basically running a single chain.
Yeah. Although if I was going to parallelize this, so that's something that I am actually actively working on at the moment, and I've not really fully absorbed the literature on it. Is if you want to parallelize this, what is the best thing to do? Is do you divide it up so there's okay, I'll have many walkers that are all adding to the collection matrix. That's one thing you could do. Or I could divide up my energy range so that I've got a series of smaller matrices that live along the diagonal of the of that band, and then build up the probability within each window, piece it together at the edges. Or do you have one collection matrix that you add everybody's contributions into before you build the multi-canonical weights? So the problem I'm actually having there is the real problem I'm interested in. The bias weights vary by. So here, what am I going? I'm going from a small number to some other small number in terms of KT. The real problem I'm dealing with, I'm spanning 2 orders of magnitude in the weights, and then that gives me when I compute. Sorry, in the bias, I'm spanning 2 orders of magnitude, so that when I compute the weight I need to reweight it to some other thing, I'm having to use quad precision to avoid falling over myself, which is, I don't know, I like to stubbornly avoid using quad precision. I feel like if you need quad precision, you've failed somehow, and you should find a smarter way of writing the code. But I should just give up and use quad precision. All right, I think that has unambiguously crashed. But you know what it's going to look like. It's going to look exactly like that, but we computed it faster. Okay, that's the take-home message. So that's all I really wanted to show you. So that's a series of increasingly sophisticated methods for more or less doing the same thing. The common theme is one simulation, or if I parallelize over energy, many simulations that are trying to sample with equal probability across an energy range, so that I've got information about all temperatures, and then I can reconstruct whatever I care about from that. Whether or not this is useful to you guys, I don't know. I guess it relies on if you're trying to, you've got some hyperparameter that isn't temperature, and you want to know, you want information about, rather than doing many simulations with a different value of that hyperparameter, maybe you can get away with doing one and doing something like this, but you have to know analytically how your probability distribution depends on that hyperparameter. So for us, we've just got beta appears in the Boltzmann weight, and so we can do this, but maybe that's not relevant so much for you guys. I don't know. Any last questions?
That transition matrix you have, so like it's sparse, right?
Yep.
Can you constrain these sparse?
Some people do, yeah. So some people, again, this is one of these things I don't quite understand why they do it, but it's probably because they didn't want to have to deal with learning how to do matrix diagonalization. If you constrain your moves so that you can only move to a neighboring bin, then there's a way of just iteratively working through each bin and working out one probability from the previous one, and then renormalizing at the end. So if you do constrain it, you can make it, a tri-diagonal matrix, and then the diagonalization will be faster, or even you can avoid it entirely.
Well, it becomes a banded matrix, right? And so, like, if you want to have, I don't know, like 5 of them, just to be able to.
Yeah, but I'm very unlikely to want 5,000 bins, right? Because I don't need 5,000. I don't need that kind of resolution on the energy. So normally I use 20 bins. Right? I was using 50 here to show that you can go to higher resolution.
I've seen in the metropolis testing that you keep a acceptance rejection roughly 80%.
Yeah.
Oh,
okay. Maybe I can say something controversial.
Statistical application, we would have much lower acceptance.
So what do you guys aim for? 2%, 23%.
There are results.
That's a very specific number.
There are results in high dimension scaling,
Yeah.
which suggest that it's under some assumptions,
which
which are definitely not.
But here he's moving one guy at a time and then
Yeah.
Oh yeah. 44%.
So my honest answer to that calculation is, as long as it's not 2% on 98%, I don't really care on a normal basis. So I think your default intuition is that you want 50%, but then I have seen some papers that have dug into details and come up with very specific numbers that are between 20 and 40. One thing that people never account for when they come up with these estimates is that at a sort of instruction level, so CPU instruction level, you are branching an awful lot when you do this. So if, like here, my model is very cheap, I'm probably doing a branch in my instruction pipeline more frequently than I'm filling that pipeline. So I'm only going to be efficient on a CPU if the CPU's branch prediction routines is getting it right the majority of the time. So really, I want something that is not 50%, because 50% is the worst case scenario for your CPU's branch prediction routine. And that's something that nobody ever accounts for when coming up with these, what is the best. But in most cases, the expensive thing is computing U. In this case, it's not, but normally your actual branch would be so infrequent that it wouldn't matter. But for this kind of toy model, or for the Ising model, for example, where each update is trivially cheap, right, to compute the change in energy on flipping a spin, then that could be a real problem, and you shouldn't be aiming for what is otherwise theoretically the best ratio, because that's going to upset your CPU. I don't know if that ever actually finished, or if it had genuinely completely crashed.
Maybe I have another question.
Oh, it did finish. It did finish. There you go. Yeah.
Oh yeah. About the synthesis, could it still be used if you're only
So if I've got this pathology and I'm looking for a way to get around it, I could just say, well, I'm going to look at the energy range that's relevant to that temperature plus just above the transition, and then I'm going to fix this problem. But there probably, if you only care about one temperature, probably doing the bond flipping algorithm is probably a better way of doing that.
asking sort of in reference to when you were musing about whether these techniques whether one needs to do single
Yeah, I mean, so I have seen this done where I only care about one temperature, but the thing I want to vary is one of the parameters that goes into U. So it might be the strength of the interaction between non-bonded beads. And I do a multi-canonical sampling where the thing that's changing between the ensembles I'm sampling over is a parameter in the model. And then that gives you a nice way of tuning the model, because you can find, well, where is the peak in the heat capacity as a function of some parameter in the model, and then refine your model to, say, match an experimental transition. Yeah, so I mean, I would call that Hamiltonian multi-canonical sampling.
There's still potentially useful if you've got if you're just interested in multimodal.
Yeah, and this transition matrix method, of course, works for anything, right? I mean, you don't have to use it to get a probability distribution from multi-canonical sampling. So in the context of ABF, for example, if you were doing ABF with some stochastic accept-reject dynamics, you could use that as a way of building up your estimate of the probability rather than a visited states method.
I guess the main difference with statistics is that our hyperparameter is not one dimension. It's not a temperature or function. It could be really hundreds.
Yes, yeah. I mean, we might have 3 if we're really pushing it, yeah.
And if you want to be critical, what is the most sensitive parameter? There are many tuning parameters here. You choose like the bandwidth, the minimum, the most one that you have really to be careful with.
I'm not sure I have a good answer to that. I can think of things where things have gone badly wrong. So things tend to go badly wrong. For example, if you stick with in the context of the Wang-Landau method, if you stick with a very high initial modification factor, then that works very badly because you're building up a very rough, rugged estimate of the thing you're trying to bias, and then that takes a long time to heal. So getting the sort of schedule right for how often do you update the bias with your current information is probably the thing that's most critical.
Yeah.
Yep.
Thanks. Thank you. Yeah, I would stop because all the optimization yeah, so we are going to the sub department.